Okay, hello, welcome, and thank you very much for attending this presentation. This is José Manuel Campos Salazar. I am with the GREP Research Group of the Universidad Politécnica de Cataluña. I am a PhD student. This presentation is about comparison of modulations and DC-link balance control strategies for a multi-battery charger system based on a 3-level dual-active bridge power converter. So then, let's get started. As outlined, this presentation consists of the following section. One introduction, then we will talk about the battery charger topology together with its control system. Then we will discuss the modulation used by the 3L3P NPC converter. Then we will show you some simulation results to end with some conclusion. Okay, so let's begin with introduction. As you know, battery chargers are required in many applications, from the cell phones to complex industrial systems. But the present, among these applications, it is worth highlight the importance of the battery chargers for electric vehicles. Battery chargers are typically classified into different categories, and the choice of each of them will depend on the specific needs of the vehicle. For instance, its power supply can be single phase or 3 phases. Depending on the location of the battery charger in the electric vehicle, it can be on or off board. They can also have galvanic isolation or not. From the point of view of power flow, they can be uni or bidirectional. And according to the technology used, they can be 2-level or multi-level. Finally, and from the topological point of view, battery chargers are usually implemented with an AC-DC stage connected in cascade with a DC-DC stage. Now, please, let me show you the battery charger topology. So here we have the battery charger topology. This battery charger is built with 2 stages, one AC-DC, which is implemented using a 3L neutral point clamp converter, I level as a 3L3P NPC converter, connected in cascade with an DC-DC stage, which is implemented using a 3-level dual active bridge converter. And this converter, that blue one, I level as a 3L1P DAP converter. Now, it is powered by a 3-phase grid and has been designed as an onboard charger, presenting galvanic isolation here, with bidirectional power flow capacity, and multi-level technology, in this case 3-level, has been used for its implementation. Finally, its lower are 2 battery packs connected in series, with which together build a battery bank. So now let me show you the control system of this battery charger. Okay? Here we have the control diagram of the battery charger. The control goals are to regulate the charging current of the batteries, IV1 and IV2, by properly controlling the B-side DC link. I mean, that voltage UVCV1 and UVCV2. The other one is regulate the AC DC link by means of the total control of the total voltage of the AC DC link. At the same time, keep the balance of these voltages. And finally, to regulate the power factor of the grid connection. Now, as you can see here, there's 2 control strategies, one for the NPC converter and another one for the dual active bridge converter. Regarding to the control strategy for the NPC converter, this is composed of 2 controllers, one based on a voltage-oriented control, and another one that allows the balancing of the voltage of the VCA and VCA2, basically. On another hand, and regarding to the dual active bridge control strategy, this is complemented using 3 controllers. One that balances the voltage VCA1, VCA2 as in the previous control strategies, and the other 2 controllers allow regulating the charging current through the control of the common and differential mode component of that charging current. So therefore, both converters have the ability to regulate the voltage of the A-side DC link, and the user can decide which option to choose to keep this voltage balance. Now, please, let me talk about the modulation used by the NPC converter. Okay, since the system is complex and involves many degrees of freedom, it is worth exploring different control options in order to optimize its performance. That's why the battery charger performance under 2 different pulse width modulation applied to the NPC converter are compared in terms of 4 figures of merits, which we will discuss later. Okay, but firstly, the nearest three vector space vector modulation NTUV is applied to the NPC converter. And then the virtual vector pulse width modulation is applied too. Okay, now regarding to the NTUV, when a converter uses this modulation, this converter can achieve a low harmonic content in the output AC voltage. Here we have the algorithm using by this modulation basically. Okay, and here we have an example where this modulation works basically in a space vector diagram. Now, regarding to the virtual vector pulse width modulation, when the converter using this modulation, this converter is capable to keep the voltage balance in all operation conditions, because each virtual vector involves an average zero neutral point of current in every switching cycle. Here we have the algorithm using by this modulation, and here we have, at the same as the previous case, a space vector diagram example where this modulation works basically. Now, please let me show you some simulation results. But first of all, let me give you some generalities, okay? This battery charger is connected to a three-phase AC grid with 400 VRMs line-to-line voltage with an lane frequency of 50 Hertz. Both converters operate at the same switching frequency, okay? Around 10 kilohertz. Now, two operating scenarios were generated according to the type of modulation used by the NPC converter. So, in scenario 1, NPC converter operate with NTUV, and in scenario 2, that converter operate with virtual vector. Moreover, the system features and performance under each scenario are studied in three cases. Case 1 means that NPC converter is in charge of balancing the voltage of the AC DC link. In case 2, dual active bridge is only in charge of this task. And finally, in case 3, both converters are in charge of balancing these voltages. Okay, and in order to quantify the performance of the system, 4 figures of merit have been defined, obtaining different values depending on the modulation used by the NPC converter. And these figures of merit are the percentage of the ripple in the DC link voltages, the harmonic content of the synthesized line-to-line voltage, the number of commutations per fundamental period generated in the NPC converter, and finally, the steady-state error present in the charging current. In order to ensure proper performance, 2 requirements are established for the system, which, of course, must be met. I mean, percentage of ripple in the DC link voltages and the steady-state error present in the charging current must be less than 1.5%. Having said that, let me show you some simulation result regarding to scenario 1, when the battery charger is in a steady state operation. Here we have the voltages of the AC-DC link, the duty ratios regarding to the leg A of the NPC converter, and the switching angles regarding to the dual active bridge converter. The same for the 3 cases, okay? So here we can see that the allowed ripple percentage is not met in any cases of this scenario. And also, we can see a low frequency harmonic component of around 3 times the line frequency in the AC-DC link capacitor voltage, which is consistent because since the NPC converter uses an NTUV modulation, hence capacitor voltage balance is achieved over 1/3 line period. And we can see the THD, which is around 41.25%. Now, here we have the simulation result regarding to scenario 2, when the battery charger is operated under steady state conditions. Here we have the same variables, but in this scenario, the allowed ripple percentage is met in all the cases. And moreover, case 2 is the lowest 1%. On the other hand, and since the virtual vector PWM does not generate third order harmonic, so the DC link voltage does not present this harmonic component, of course, right? Finally, the THD in this scenario is around 50.23%, which is bigger than scenario 1. Finally, the ratio of the number switching of the NPC converter between scenario 2 and scenario 1 is 4/3. That means that the battery charger operating in this scenario, the switching losses increase, basically. Okay, now please let me show you the dynamic under step change of the reference charging current under case 3, but for both scenarios. Okay. Okay. At the startup, the reference current are set to 100 amperes for both scenarios. Okay. Then at 150 milliseconds, there is a step change in this current, taking the values of 70 amps and 130 amps. Finally, at 250 milliseconds, a second step change occurs in this reference, okay, taking the final values of 130 amps and 70 amps, respectively. And from the scenario 1, we can see that the charging current includes an oscillatory component at low frequency that has been transferred along with the battery charger. Can you see here? And finally, the steady state error of the charging current in scenario 1 is around 4.6%, and in scenario 2 is almost neglected, almost 0. Having said that, please let me give you some conclusion. Okay, a battery charger configured with a 3-phase, 3-level NPC AC-DC converter in cascade with a 3-level dual-active bridge DC-DC converter and connected to 2 batteries in series has been presented. Now, a control scheme has been configured which allow, on the one hand, to control the total voltage of the AC-DC link and at the same time to balance the voltage of this DC link, and on the other hand, regulate the charging current of each battery. Now, when the battery charger operate in, or when the NPC converter operate with virtual vector, EWVM, the battery charger presents a larger capacity to balance the AC-DC link capacitor voltages and to regulate the battery charging current. Now, when the NPC converter operates with NT-UV, this battery charger presents a reduction of the harmonic distortion of the line-to-line voltages generated by the NPC converter, and it also presents lower switching losses in this converter. So this is my presentation. Thank you so much, and bye-bye.